situations where everything works for harmonic oscillator. So this is a disaster in harmonic oscillator, where of course classical Wigner model is exact. The classical fidelity will give you the same. So here the semi-classic would actually be worse. Okay, so any questions about this? So let me go back to electronic spectroscopy. So again, we are trying to improve, we are not very ambitious, we are only trying to improve on these global harmonic models. Let's see how it works. So we want to model experiments, but there could be many errors, so actually it's nice to compare with exact quantum. So here is a Morse potential. It's not in very anharmonic region. You know that, of course, in Morse potential you can also run into trouble. But if you use the vertical harmonic, you are a little bit off, you have wrong spacing. If you use adiabatic harmonic, you get the wrong amplitudes. And with the Saar Gaussian, you improve on both. And again, this is not very anharmonic region of the Morse oscillator, but you can improve there. And most molecules are actually a little bit like this. So here is ammonia, which by the way looks completely anharmonic, right? If you look at the potential energy surface, it's nothing like a harmonic oscillator. And again, this is the nuclear semi-classical wave packet computed ab initio. And the results are pretty encouraging. You know, it's not perfect, but you get quite nice agreement with the experimental spectrum. If you use the vertical harmonic, you get the wrong peak spacing. If you use the adiabatic harmonic, you get the wrong amplitudes. And I just want to say there is one thing in which the TGA is worse than the global harmonic models, and these are these negative features. They're not so bad here, but they can become worse if you do longer propagation. And the reason is, of course, because the effective time-dependent potential is time-dependent. So you are not guaranteed to conserve energy, and you are not guaranteed to have positive definite spectrum. Whereas in these models, they use completely wrong potential, but it is time-independent. Okay, so this is much more interesting problem. It's electronically forbidden spectrum of benzene. And here you cannot propagate a Gaussian. You cannot use the so-called Condon approximation, which is this dotted line. It would just get no spectrum at all. That means electronically forbidden. You need to propagate a Gaussian times a polynomial. And, but this is actually quite easy to extend. And again, if you use global harmonic potential approximation, you would get the blue spectrum with wrong peaks and wrong amplitudes. And with the Saar Gaussian, you get almost perfect amplitudes. And this spectrum starts to be quite resolved. As you notice, the peaks are quite narrow. And these gray peaks, which cannot be reproduced, are hot bands, which are due to finite temperature, which we so far ignore. Okay, so what is the idea here? It again goes back to Lee and Heller many years ago, that you can propagate polynomials times Gaussians pretty much at the same cost as a Saar Gaussian itself. So if you use the local harmonic approximation, the form of the wave packet remains. The only thing which you need to do in addition is propagate this linear factor. Okay, and but ab initio cost is 0. Okay, so maybe I would like to mention one thing which is, you know, maybe sounds like a little bit technical detail, but to compare with experiment, you need to do orientational averaging of the spectra, rotational averaging. Because in a gas phase, the molecules can be arbitrarily oriented with respect to the electric field. And so it is actually ignored by most theoretical calculations. If you have the Condon approximation, you just align the molecule with the field, compute the spectrum, and divide it by 3. But if you use this approach, which is for non-Condon approximation, then it's not valid. You cannot do this. And it almost looks like that you would have to numerically average over all orientations of the molecule. But you can quite easily show analytically that you don't need to do this. And you can just compute the spectra for 3 different arbitrary but orthogonal orientations of the molecule and get the right spectrum. And this is, again, computational at no additional cost because it uses the same ab initio trajectory. So to show that also we are not ignoring, you know, some geometrical properties, all these algorithms preserve a Liouville theorem and symplectic structure with machine precision. So we also worry a little bit about this, but this is not so difficult to take into account. And So now I want to tell you about some new things. And so I hope I persuaded you that the simple thought Gaussian approximation is actually useful for some things which are relevant experimentally. But can we do worse than this? And again, the answer is yes. And otherwise, I would not be here to tell you about it. So what can one do worse? So the worst thing is I told you that the Hessian is extremely expensive. So here almost nobody uses ab initio electronic structure, but imagine that I give you a function of 100 variables. Can you tell me roughly how much more complicated will be the gradient or the Hessian? So I would say maybe except for exponential, it will be d times more expensive the gradient and d squared times more expensive the Hessian. So really you want to get rid of the Hessians. Nobody wants to do calculations where you need to compute more than one Hessian. And so the idea here is that you use a single Hessian approximation. But this is not that you use global harmonic model. The trajectory follows the exact potential, but for the semiclassical propagation, you expand the potential to a quadratic degree, but with a single Hessian. So you use energy and gradient exactly, but the Hessian is one fixed. And you have two options, vertical or adiabatic Hessian, which I mentioned before. So actually, you can even use a third one, which is the initial one, which you use typically for finding the initial state. So there are these three natural choices. And so in some sense, you can look at like this. Here in our community, we are usually worried about really accurate semiclassical approximations. Here I'm really thinking about the bottom of this ladder. So, but I told you already that even global harmonic approximations, there are much cruder ones than the one which I was showing you. Then there is a thought Gaussian approximation. Typically, people interpolate Hessians. And I told you this is like a drastic interpolation. We just use one Hessian. But one Hessian is actually often better than using 4 or 8. And let me try to explain why. So as I told you, TGA doesn't conserve energy, which is not surprising, but because the effective potential is time dependent. So if you look at the time dependence of the energy, you differentiate the expectation value with respect to time. Because the wave function satisfies Schrödinger equation, you can put the derivative just on the Hamiltonian, okay? Then, of course, kinetic energy is time independent, so you just differentiate the local harmonic approximation for the potential. And then you use nice trick, this chain rule, the time derivative with respect to the coordinates, and there are beautiful cancellations of the energy, gradient, Hessian, but one thing which you cannot cancel, and the only thing, is the third derivative of the potential, so that the energy changes according to the trace, where you have the third derivative of the potential and the covariance of the wave packet, position covariance. Okay, we also heard about that one. Okay, so the energy is not conserved, but the single Hessian thought Gaussian approximation, even though it has time-dependent effective potential again, it actually does conserve energy. So it is a little bit funny. If you do the same procedure, you will find out that the derivative is proportional to this expectation value, but this BT is just a vector which you can take out of the expectation value. It's a vector of numbers. It's not an operator. And the expectation value of Q is exactly QT, so this thing cancels, and you get 0. And you can see it nicely in this picture that the TGA energy grows, but if you use the adiabatic, the global harmonic approaches, or the single Hessian TGA, the energy is exactly conserved. So there is actually, in this drastic approximation, you gain something. And in fact, you gain a little bit more. So if you look at TGA, you can split the energy into the classical energy of the center of the wave packet and the rest, which you can call semi-classical. So the energy of the center trajectory is just the Hamiltonian evaluated at the center. And the semi-classical contribution you can also evaluate analytically. It's connected to the width matrix. This expression is a little bit ugly, though. Okay, but you can see, you can compute it, and you will see that the classical energy is exactly conserved. So this is the red line. It's exactly conserved because it uses the exact time-independent Hamiltonian. But the semi-classical one uses effective time-dependent Hamiltonian, and it goes up. But this splitting is actually very interesting. So in practice, you can evolve stability matrix, or equivalently, you can use so-called PZ method. that Rick used, again, 40 years ago. And it's very closely related to Hagedorn parametrization. It's a beautiful trick where you split the Witz matrix, complex Witz matrix, into a product of two complex matrices, which are intentionally called capital P and capital Q. And you make this ansatz. Actually, you have a lot of freedom how to choose this P and Q. But in all cases, they satisfy the Hamilton's equation of motion for the linearized dynamics. So these are not vectors, but matrices. They're complex. And the gradient of the potential is replaced by the Hessian. It turns out their Hamilton's equation of motion in this form of a more fancy Hamiltonian. Just notice that you have to use a complex conjugate of these matrices in the Hamilton's equation. This is generally true for complex Hamiltonians. But then you have this Hamiltonian for the new capital Q and capital P matrices. It's effectively time-dependent because it depends on the position of the wave packet. So again, we have not gained too much, just more understanding. Okay? But what is really amazing in the single Hessian approximation, the semiclassical Hamiltonian doesn't depend on the QT, so you can just add it together, and you get the Hamiltonian in 4 variables, and all the equations become Hamiltonian equations of motion of this new classical Hamiltonian. Usually people use different initial conditions, different parametrization, even in the Hagedorn parametrization. But we have found one where you get the initial, so the expectation value of the energy is exactly equal to the classical energy in this new system. And this is also connected in a beautiful way to book by Kramer and Saraceno here, where this is actually true if you use variational principle to propagate Gaussian wave packets. This is always true. The only difference is that the Hamiltonian cannot be split into 2 contributions, so that the whole energy is conserved. So you can map a variational solution of a Schrödinger equation. Actually, it doesn't even have to be a Gaussian wave packet, but in general, you can map it to a classical Hamiltonian systems in the parameters, and the Hamiltonian is defined simply by the expectation value of the Hamiltonian in the wave function, which I think is absolutely beautiful. And of course, it becomes nonlinear, so that's variational principle leads to nonlinear equations. So here there is a similarity. The problem with Gaussian wave packets propagated variationally that you need to, it's much more difficult because you would need to compute expectation value, the gradient and Hessian of the potential in the Gaussian. So, okay. So let's just see how it works. This is again Morse potential. If you have very weak harmonicity, you don't gain anything. The TGA is pretty good. The adiabatic harmonic is pretty good, maybe a little bit worse. And the single Hessian is actually pretty good too. It turns out slightly better than the TGA, but you would not expect that always. Okay? But now if you increase anharmonicity, the third Gaussian approximation becomes worse. The adiabatic single Hessian approximation also becomes worse, but both of them are not too bad. Adiabatic harmonic is much worse. You lose some peaks almost completely. And you can look at this more rigorously to look at the error of the spectrum measured by this quantity. It's basically scalar product with the exact spectrum. And you see that if you use the vertical harmonic approach here, that the error is very big for all anharmonicities. And if you have very weak anharmonicity, the third Gaussian becomes the best. But the single Hessian third Gaussian approximation actually wins if you increase the anharmonicity. And the explanation is very simple. As you all know, that the third Gaussian can really unnaturally spread too much. But this one, in the single Hessian version, it becomes like a squeeze state. It feels a constant Hessian, so it can breathe, it can stretch a lot, but it's limited, the stretch. So in the end, it may be also okay. All right? So here is a practical example of it, again with ab initio electronic structure. And now I think this is really the method that finally could be useful for somebody to use easily because you just have one Hessian. And again, this is a third Gaussian approximation, which is pretty good. Maybe not perfect here. The adiabatic single Hessian is actually slightly better. It has less negative features, which we understand completely. It can still be negative because you have the time-dependent potential, but because you conserve energy, it is less important. Here it turns out to be better almost everywhere, but this is not expected. and the adiabatic harmonic is the worst. So this one is pretty much as expensive as this one. Well, actually, it's more expensive. Here you need one Hessian, here you need one Hessian and one trajectory. But here you need one trajectory and Hessians along the whole trajectory. So, so I think this may be, it's very crude, but maybe useful in practice. And I want to show you that you can use it for more complicated systems. So for example, you can look at time-resolved electronic spectra, where the spectrum is resolved both as a function of frequency and time. So this is quite straightforward, it's all Gaussians, and I think actually I expect even more, that it will be even more accurate compared to experiment, because this is much more resolved than typical experiments. And then this is another example of connection to Loschmidt echo, because in time-resolved experiments, your initial state is not a stationary state. One laser pulse excites the wave packet, it moves for some delay time tau, and then it is probed by another laser pulse, and after that, you have to propagate the wave packet on both states. But it is stationary on neither of the two surfaces, so this is really a perfect example of Loschmidt echo. So again, all the approximations for Loschmidt echo might be useful here, except for the dephasing representation, because it's close to harmonic, unfortunately, most of the situations. Okay, so the last thing I want to mention quickly is that you can use it for larger systems. So it's really, now this becomes non-trivial. Again, if you use global harmonic model, it's a bit bad. If you use even the thought Gaussian approximation, you get a pretty good agreement with the spectrum, and you can go all the way to 100 degrees of freedom. But I think with the single Hessian version, we could do maybe 1,000. Okay. But now the question is, actually, a lot of people confuse complexity, not here, but a lot of, let's say, computational chemists confuse complexity with the number of degrees of freedom. And you see that this has 105 degrees of freedom, but the spectrum is very simple. So the question is, how do you understand it? We made a brute force calculation in 105 dimensions, but can you understand it more simply? So this is a little bit connected to what Steve mentioned. So it's also connected to the question, can you hear the shape of the drum? And you cannot. You can have isospectral billiards. So it's a similar, if you have a spectrum, can you understand what is the dynamics, what is the potential underlying it? And what is really funny that many people, even if they use anharmonic method, full semiclassics, in the end, they use harmonic language to interpret the spectra. So they use normal modes, harmonic analysis, and so on. Yeah, that's true. If you look at the amplitudes, right? So this is actually, my whole talk was about amplitudes, because there are much more sophisticated methods to get the positions of the peaks, but they usually don't worry about the amplitudes. And I don't worry so much about high resolution, but about the amplitude. So I don't have time to go into the details, but the idea is simple. The single thought Gaussian approximation requires something about stability, uses the stability matrix. And once you have the stability matrix, you have really a lot of valuable information, like Steve mentioned. And so first, what you can do is decouple the modes into approximately uncoupled groups. So here, each dot corresponds to one vibrational degree of freedom, and the edges of the graph are the couplings. And the longer the edges, the weaker the coupling. So just by looking at this, you can immediately see that you can prune it, you can cut it here, cut it here, cut it here, and you would get much simpler problem, which you can use with, you can apply quantum methods even to solve it. But you can actually go much further and decouple it much more. And then you can also look which degrees of freedom are most important. So these are the thick dots, thick vertices of the graph. So you can really reduce the dimensionality drastically. And let's see how it works in practice. So this was the spectrum computed in a brute force with 105 dimensions. By this dimensional reduction, you can make automatically, with the black box, without any intuition, you can make a 8-dimensional model, which gives you almost perfect spectrum, and it's intentionally not shifted. And then, if you are not interested in the broadening, but only on the position of the main peaks, you can go back down to 4 vibrational modes. So now people are talking a lot about, both in electronic structure, in condensed matter, about this tensor method and hierarchy tensor decompositions. And this is kind of, and also in quantum dynamics, for example, multilayer MCTDH and so on. And they always construct these trees, how you decouple modes, but they use the intuition about it. And here you can kind of generate the tree for the decoupling automatically by changing the threshold of the coupling. Okay, so I have 1 minute. Okay, so maybe the last thing I want to mention you, how do you project into few degrees of freedom some potential which depends on 100 variables which are arbitrarily coupled? And for example, the action. In the action, you have potential which is a function of 100 variables. So how do you assign the action to some degrees of freedom? And actually, it's maybe not perfect, but there's a quite nice trick. Using conservation energy by Hamiltonian dynamics, you can write down the Lagrangian as twice the kinetic energy minus the energy. And because the energy is conserved, and initially, in this case, it was just a potential, actually it's okay if it's also the kinetic energy, but it's just a number. So the kinetic energy you can easily project into few degrees of freedom, and this one just gives you overall phase which grows linearly with time. So it's very easy to partition it among the modes. It took us some time to realize this. You don't have to make the model first before you do the calculation. And with that, I would like to conclude. So we feel like we have revived, over 40 years old method, the thought Gaussian approximation. And of course, unless you use two thought Gaussians, you cannot describe even a double-slit experiment or really serious interference. But electronic spectroscopy, where you have autocorrelation function, there is no classical analog. It is really quantum phenomena, whereas vibrational spectroscopy, you have a dipole-dipole correlation function, which have a classical analog. So I think it's interesting that you can actually do something with it. And it's not, sometimes I'm even surprised how well it works. I showed you a new approach to analyze spectra and reduce dimensionality, although not in details. And then I think what I'm excited about is this single Hessian thought Gaussian approximation, which surprisingly conserves energy, has Hamiltonian structure, and it's almost as accurate, in some practical examples as the thought Gaussian itself. So thank you for your attention.
Questions?
So could you explain to us